credit card. You kind of move it around and you can see that hologram. That's a diffraction. It's obviously a different pattern. You get the maple leaf or whatever. Here we just split it into 6 beams. And the principle we use is the efficiency of that diffraction. How bright this spot gets out here depends on the height of the lines. So you make the lines of an antibody and an antigen binds that you're trying to measure specifically, the spot will get brighter. And the purpose of this prism here is we can actually monitor this in real time. So we make the lines out of avidin and biotinylated antibody binds. We can follow that binding and characterize it, or use this delta to understand how much was there. We can introduce subsequent steps, capture antigen, measure that, and we can actually look at how it associates, which is useful in certain diseases. And this whole thing, because of the prism that's here, all the samples up here, so we can do all of that without going through the samples, so we can monitor that in real time. So what we've done is built a research instrument and then a series of clinical instruments that basically deliver the sample, that deliver the solutions there, monitor this in real time, and applied this to a variety of applications that I'll show you in a moment. The Ziplex technology, we like our X's, and Z's, and Z's, and our titles here. As I mentioned, is an array. Basically, on the tip of that little pipette is an array with about 500 features on it. Each of those features has got about 70 channels of a 10 micron size that allow flow through it. And that basically allows you to use that in an automated fashion and do things like hybridization much faster than you would using a traditional array. And now, what's the value of that? Now this makes it practical to take those research tests and move them into a clinic and run them routinely. And start to look at things like infectious disease. So here we have a chip where we can monitor, we can screen. This is a project for screening immigrants at point of entry to see what their status is in terms of whether they need treatment or whether they need their vaccinations updated. So here we're looking for the presence of antibodies against all of these pathogens in one slide. Here we're actually using the real time to be able to determine whether a pregnant woman has an acute infection of toxoplasmosis, a parasite, or whether she's been exposed in the past. And the difference there is the fetus is tremendously susceptible to damage if there's an active infection. So decisions need to be made in the first trimester about treatment or other options. And basically by looking at how much antibody is present against that parasite, and then how easily it's washed off. You can tell how strong that antibody population is, or the avidity of that antibody population. And if it's really strong, it's been around for a while, it's a chronic infection, you don't need to worry about it. If there's a really weak antibody response, it means it's new, and it's a current infection, and you need to deal with it. And the real plus here is, this is about a 30-minute test. Right now, it's a 48-hour test. So this was developed in particular with a group down in Texas with a walk-in clinic with pregnant women, and their problem was they'd take a blood sample. By the time they got the results, they could never find the person again to actually follow up on it. So they needed a test that could be done right here. In Canada, people with an OB/GYN, you can phone, follow up, but in many parts of the world, they don't have that luxury, so you need an immediate result so that you can act on it. I mentioned the cancer. So our first clinical product is an array which predicts breast cancer recurrence, so how aggressive after surgery an individual needs to be potentially treated in order to prevent recurrence of disease. And really the upside here is not the need to have unnecessary chemotherapy in those cases. And I talked a little bit about the ovarian cancer. On the protein side, typically there, we're looking more at early detection. So these are serum samples as opposed to taking a sample from tissue that's been removed during surgery. And we can monitor either the response to drugs, panels, in this case, again, ovarian research. These are proteins whose genes have been changed in expression and are now converted to proteins that we can pick up in serum and monitor them in a simple fashion using the DotLab platform. A very exciting area, and I promise this is the last of the science slides, is autoantibodies. So again, looking at antibodies, in this case now looking at antibodies, the body's formed against foreign tissues in its own, within itself, against the host. one of the most common is the autoimmune diseases. But in cancer, as tumor cells begin to form, then the surface of that tumor cell is foreign to the body and will create antibodies against self-antigens or autoantibodies. And it's been now shown that as few as 600 tumor cells can generate enough of an autoantibody response that it can be detected by this technology. So that's well before we would ever be able to see it on imaging. And I had the privilege a number of years ago of working with Dr. Judith Folkman at Harvard, who demonstrated very clearly that if you can detect these tumors at this size, that basically low doses of the chemotherapy agents we have now without preventing new drugs can be very effective at preventing their growth. He did that in a pediatric environment and showed that it can be extremely effective. So these technologies, I think, can have a tremendous impact on health care by moving detection, a better understanding of disease, moving detection much earlier. The last is here we can actually see viruses directly. So this is some work we're actually doing. If H1N1 comes back this fall, we may get tested on one of our instruments as part of a research trial within the OAHBP, formerly the Ontario Public Health Labs, where basically we've developed a 4-plex test to be able to take a nasal swab and in 30 minutes figure out not just that it's viral, but figure out which strain it is. Now the importance of that and the reason for this clinical trial is some strains of H1N1 are resistant to one drug, some are resistant to another drug. Right now you just kind of guess and give one, and that has been shown to begin to start to drive drug resistance and changes in the virus. So what we're trying to test is if you can tell exactly what that strain is before you give the drug, can you actually change the outcome and prevent the development of that resistance? So the last slide, this is kind of my, I don't know, just some thoughts that have affected me. But I think it's really, if I look back on the opportunities that I've had, science has been much more about science. I've always been in science, but it's really the principles of science that have allowed me to do what I've been able to do, whether that's on the business side, financing side, managing people. I think the process that you go through to learn kind of logical problem solving can be applied so broadly. And if you think about, the experimental method where you set something up, you observe it in order to understand it, and then you basically influence, change a parameter to look at what happens again. That really describes how you manage people, how you close a sale, how you get a deal done. It's all about observing what people are doing, observing the situation, being able to sit back objectively and understand that situation, which I think you learn from a good background in science, and then being able to use that information to influence. As I mentioned earlier, the ability to partner that with a well-rounded sort of social skills and the ability to talk. I'm not maybe the best example of that, but it is really going to make a big difference going forward. I had the luxury of having about 45 PhD level scientists working for me when I was in Europe, and they clearly fell into two groups. They were all really smart, really good scientists, and these were all field scientists working with customers. One group, really good science, they'd see the problem and they keep working at it until they could solve it scientifically. The other group would see the problem, they'd look at the bigger picture, figure out what the customer needed to do, and understand whether that was the problem that really needed to be solved. And I think a lot of that insight comes from social interaction and the ability to understand as opposed to just being a really good scientist. The skills, I think, are broadly applicable. It doesn't matter if it's academia, industry, technical. Again, Alex, my wife, they hired a whole bunch of music students from WLU for their IT department, and they had no computer background. And that's because they had a broad set of skills to be able to understand and think broadly. And I think the same thing goes with the science background, I think, for the areas of business and particular management. The business of life science is booming right now. Unfortunately, in Canada, there's not a lot